Class, nakikita nyo na yung presentation?
Yes, ma'am.
Yes, ma'am.
Okay,
Yes
thank you.
po.
So, basic, thank you. Basically, in our first slide are the different types of waveguide that we have. Okay, so mare-recall ninyo, we have circular, we have waveguide, and we have what do you call this? The rectangular, the circular, and our rigid, and what's the we have the flexible na mention ko, circular na mention ko, rectangular, the rigid, and the elliptical. Yung elliptical lang di ko na mention. Okay, so basically, we all know that waveguide is used to carry the energy from one point to another, but it is specifically used for microwave signals from the antenna to a receiver. It is preferred in microwave communication, and ang difference niya sa ating transmission line is that it has no center conductor. It is a hollow metal tube, tapos yung gitna niya, okay, walang laman. So yun yung main difference niya. Because yung walls itself ng waveguide ang nagsiserve as conductor para dito sa ating channel na ito. Okay, so as mentioned, waveguide is a hollow metallic tube of uniform cross-section for transmitting electromagnetic waves by successive reflections from the inner walls of the tube. So ang mga dapat nating tandaan dito, uniform cross-section at ang propagation mode sa kanya ay successive reflections. So ginagamit lang siya for frequencies above 1 gigahertz because waveguide will only carry or propagate signal above the cutoff frequency. So, below the cutoff frequency, walang reflection na magaganap sa ating waveguide. As you can see, dito sa ating image, ang pinakita dito is the rectangular tsaka circular waveguide. And we all know the properties nitong dalawa. Okay, mga cross-section nila ay naka-uniform in size. And then dito sa baba, pinapakita kung paano natin ginagamit si waveguide to connect yung one point ng ating system to another point from the transmitter to the receiver section. Just like the simple definition of what a channel is, it carries the signal, okay, from the transmitter to the receiver. It is just that nagkakaiba-iba lang yung property nila depende sa kung ano yung signal na i-carry nila. Just like the fiber optic, light yung kanyang i-carry. Dito naman sa waveguide, okay, i-carry niya yung ating electromagnetic. It's either transverse electric o kaya transverse magnetic lang. So doon nagkakatalo-talo yung iba't iba nating channel. So it was invented by George C. Southworth, and being a known inventor, he was awarded with the Morris and Liebman Award, the Stuart Ballantyne Medal, and the Louis Levy Medal. So ito yung contribution niya na ni-recognize ng iba't ibang award-giving body at pinangunahan in 1938 ng IRE, International Radio Engineers. So dahil sa contribution niya for the field of radio physics. Okay, so ganun kahenyo. So parang ano siya, an inspiration to us, lalo sa inyo na nagtithesis ngayon, na sana yung mga output ninyo ay maging isang masterpiece at kilalanin na in the near future, it will be the backbone of the future technology po natin. So, to simplify, ano si waveguide versus sa iba? Okay, si transmission line versus waveguide. So, kapag na-understand mo yung table na to, masasabi mo na natutunan mo na ng husto yung mula sa umpisa ng transline hanggang dito sa ating huling topic. So, the transmission line supports transverse electromagnetic waves, meaning, okay, both the action of signal and the relationship is transverse or perpendicular to each other. While the waveguide it can only support one of them. It's either transverse electric or transverse magnetic. Also, the transmission line can pass all frequency through it. Samantalang si waveguide, it has the so-called cut-off frequency, if you remember. Okay? It is the lowest frequency possible to pass through. The lower frequency than the cut-off cannot pass through. The higher frequency above the cut-off can continuously pass through the waveguide. Yun yung concept niya. Samantala in transmission line, kahit sinong frequency, padadaanin niya except that kapag na-meet na niya yung limit for that transmission line, losses becomes observable. Okay? Habang tumataas yung frequency, okay, nako-convert yung loss into heat. Nalalaman mo lang na hindi na sapat, hindi na tama yung dumadaloy kasi umiinit na yung conductor mo. Transmission line is a two-conductor transmission. Okay? Yun nga lamang ang conductor niya, it's either balanced or unbalanced. Dito sa waveguide, there is only one conductor transmission and it is the wall of the medium. In transmission line, reflections are less, while in waveguide, okay, so ginagamit niya mismo yung reflection as mean to propagate the signal. Samantalang in transline, pag sinabing reflection, ibig sabihin loss po siya. In transmission line, it has a characteristic impedance, while in waveguide, okay, hindi na siya characteristic, it's the wave impedance. Sa characteristic impedance kasi, it's the conductor and the whole transmission line itself that has impedance or constant opposition to the transfer of energy. Samantalang sa waveguide, it is not the wall. Okay? Kung hindi, it is yung wave itself that has an impedance. Transmission line propagation of waves is according to circuit theory, meaning it is in terms of voltage and current. Sa waveguide, it is more complex because the propagation is according to the field theory, meaning pinag-uusapan dito ay yung electric field at magnetic field. In transmission line, it has a return conductor to Earth, while in waveguides, it acts as Earth. So siya na mismo, nasa kanya na lahat. Then trans bandwidth limited, as well as all frequencies true, while in waveguides, the bandwidth is limited, depending on the construction and dimension of the walls. In waveguides, the waves get dispersed. So yun basically yung difference na
Ma'am ba yung nawala?
Nawala si ma'am.
Naging host na ako kahapon eh.
Oo, nalog ata siya. Sa kanya tayo.
Putol-putol din ba siya sa inyo?
Oo,
Oo.
Boses.
Mm.
Ano, live ba dito? Ba't naging host yung akin?
Taka mo na, Des. Commercial break, Des. Kataka mo na.
Desma, tingin nga your face. Sample.
Uy, baka may gusto sumali acoustic, oh.
Ikaw, pag acoustic ka eh.
Ano yung grounded? Ah, sorry.
Ano, no?
Grounded. Kaya utay pala yung kala ko sa headset ko. Oh, ano.
Ahead. Uy,
Ito lumiraw, pre.
Ano si Tolome, pre?
Autistic night.
Tama ka dito ba? Nawala si ma'am.
Na-DC daw,
Tapos na
converge
klase.
problem.
Puta, may klase na pala.
Converge problem.
Yawa, Rusty.
Uy, kung sino man. Rusty, balik mo na. Ito naman.
Kakapasok ko nga lang, pre.
Kinik niya si Ma'am.
Kala ko, na naman eh.
Rusty, kinik mo, no? Mamaya, dito.
Patay tayo dyan.
O yung mga songers natin dyan.
Kanta
Baka
naman
naman.
kayo.
Acoustic dyan, oh. Sino ba?
Okay, class. I'm sorry. Pasaway na converge to. Can you hear me?
Opo.
Medyo
so
mahina po, ma'am.
mahina. Saan ako natapos?
Sa yung ground po ata. Ay, yung ano pala, yung earth.
Ito.
Eto.
Yes, ma'am.
Grabe ang haba
Ay,
na na
Ay, hindi
sinabi.
po yung sa bandwidth na po, ma'am.
Bandwidth ba?
Opo.
Bandwidth is limited. Ay, nako, Diyos ko, pakisama ka, Converge. Okay. So, in transmission lines, waves do not disperse, while in waveguide, nadi-disperse po or kumakalat yung wave kasi nga because of the reflection. At yung dispersion na to, mamaya madidiscuss din natin sa kanyang loss, which is scattering. Pag message nyo agad ako dun sa group natin sa GC kapag nawala na naman ako, ha? Pa-blatter nyo ako. Okay, so advantages of waveguide. So, siguro na-mention na ito sa inyo, madali siyang i-manufacture, meron ka lang parts, may dimensions, may waveguide ka na. Okay, it is for handling large power up to kilowatts range. Okay, power loss is negligible. And pag tinanong bakit, it is somehow because of yung kanyang hollow center, because kung i-recall natin in the topic transline, kapag air yung dielectric, yung heating loss becomes negligible. Then, because of this, very low loss ang attenuation niya. And when it travels, okay, may nag-message din, si Rapada, hindi makapasok, nagloloko internet namin. Pareho po tayo. Okay, so it experiences lower losses than a coaxial cable. So yun yung advantages niya. For the disadvantages, ang dami niyang special couplings na kailangan, katulad nitong nasa picture. And these couplings require specialized instrument din para magamit. Okay? yung physical size niya becomes a limitation, lalo na kapag ang pagde-deployan mo ay sobrang layo. Okay? Then the cost is high because of the nature or yung properties ng materials niya. It has weak thermal stability dahil nga fully metallic tubing po siya, madaling kapitan ng init yung kanyang surroundings. And the 3D waveguides implementation is difficult. So ito po yung iba't ibang mga coupling units na ginagamit natin para dito sa waveguide. Then, applications of waveguide. We use it for optical fiber communication. At kung makikita ninyo, ang waveguide po dito is yung structure na ito, the single mode waveguide. For the photonic IC, pag sinabi natin photonic IC, it works with light instead na electrons na ginagamit ng ating conventional integrated IC. So, ayan, kung makikita nyo, we have here the 3D waveguide na ginagamit for this photonic IC. Then, it is used for broadcasting. Okay, so kung makikita nyo rito, ayan po yung beam waveguide. Papunta doon sa pinaka-microwave antenna natin na ito yung reflector niya, sub-reflector. Yung kabuuan niya, it's the microwave antenna. Okay, in our microwave oven, it is used as a medium din po sa loob ng ating microwave. At ito po yung masarap na ulam sa loob para maluto po yung manok. Then of course, as we all know in the spacecraft, nandun po siya papunta dun sa mga antennas na ginagamit natin and the solar panels. Then, we all know na ito yung different forms and types ng ating waveguides. At sa bawat isa, meron siyang iba't ibang characteristic, kaya ganun siya hinulma na shape. So, una, yung rectangular waveguide natin. Okay, so rectangular, meron siyang dimension na A para sa base niya and B para doon sa height niya. Then dito sa image sa kanan natin, okay, nasa pinakaloob niya yung ating A and B na dimension. Itong nasa labas niya ay ginagamit para ma-mount siya ng husto at pang-protect na din, pang-interface niya kung saan man i-connect tong waveguide na ito. Pag sinabing rectangular, it is the dominant mode or the dominant configuration sa mga waveguide. Usually ginagamit natin sa radar system, sa mga equipment shelter. At bakit kailangan rectangular? Kasi makapal yung wall niya, mas makapal usually kesa sa circular waveguide at madali siyang i-mount. Okay, compare dun sa iba nating mga waveguide. Sa circular naman, ginagamit natin siya kapag kailangan natin ng simple installation at saka kapag kino-consider natin ang wind loading. Okay, bakit? Pag sinabi pong wind loading sa engineering, meron pong 3 loading zone ang ating bansa. That is the light loading, medium loading, at saka heavy loading. Ano yung tinitignan na load? It is the wind velocity. Kailangan kapag light loading, the expected wind velocity is 160 km per hour. Kapag medium loading, it's 200 km per hour. At kapag heavy loading, it's 240 km per hour. Ngayon, kapag nagde-design po tayo ng communication system such as antenna, towers, ang minimum loading requirement sa design is 200 km per hour or yung medium load. At napatunayan na yung circular ay mas kaya niya ng strength niya na i-withstand itong mga wind loading na ito. Basta perfectly shape yung kanyang circumference or lahat ng areas at mag-fit in siya, walang mga unfitted loss na mga tinatawag. So, yun yung tandaan natin. Pag wind loading, gaano kalakas yung hangin, ano yung, kaya dito binabatay, ano yung strength requirement ng mga materials na ginagamit natin kapag nag-i-install po tayo. So, basically, yun yung application ni circular waveguide kapag kino-consider mo yung wind loading po natin. Next, we have the elliptical waveguide. So, mapapansin natin, meron siyang helical corrugations. Okay, so si elliptical, ang purpose naman niya, madali po siyang mabend. Okay, so madali siyang i-handle kung gusto mo siyang i-connect, i-bend-bend mo lang siya. And usually ginagamit siya for microwave feeders po natin sa ating mga antenna system for microwave communication. Si rigid waveguide po naman, so kung makikita nyo, meron siya mga ridge na nagpo-protrude either sa taas lang o kaya sa baba. So, because of this ridge, nalolower niya yung impedance ng ating um, waveguide, then yung kanyang bandwidth, nawa-widen naman po niya. So, another characteristic niya, it has low cut-off frequency, pero ang disadvantage niya, mababa lang yung power handling capability niya. So, kung kailangan mo ng higher power, gamitin mo yung circular o kaya yung rectangular. Kasi itong elliptical, since meron siyang soft part, okay, at may bending, mataas naman yung bending loss po niya. Si flexible waveguide naman po. Okay, so meron siyang spiral wound ribbons at may brass copper po na ginagamit sa kanya. Meron din siyang, kung makikita nyo, balot siya ng kulay black. Ayan. Ang tawag doon ay soft dielectric coating made from rubber. So, ginagamit to para hindi siya mapasukan, okay, lagi ng tubig o kaya magkaroon ng insertion ng unwanted air na pwedeng mag-produce ng kalawang doon sa metallic part niya sa loob. Then, ginagamit ito usually sa mga microwave test equipment. Okay, paano nag-ooperate ang signal sa loob ng waveguide? So first, it must have a phase velocity. Dalawa yung klase ng velocity sa waveguide, phase at saka group velocity. So yung phase velocity, it is the rate at which the wave changes in phase in order to undergo a phase shift of 2 pi radians or 360 degrees. Ang requirement kasi ng signal is magkaroon ng phase shifting na ganon. So, it is the velocity with which a wave changes phase in a direction parallel to a conducting surface such as the walls of the waveguide. While doing the shifting of 2 pi radians, it must do it in parallel manner. The rate of phase change at 2 pi radian is to be considered in the derivation of equation for the phase velocity. So dito, nakikita natin yung difference ng phase velocity at makikita nyo na nasunod niya yung requirement that the direction must be parallel to the conducting surface. Ang conducting surface natin ay yung wall. Okay, then yung group velocity, it is yung maraming waves sa loob ng waveguide and ano yung amount ng velocity na ginagamit para sa kanilang propagation, which will later describe further. Okay, so this is the equations for the phase velocity. It is equal to wavelength over time, or it is equal to wavelength over times the frequency, and it is also equal to, okay, pag sinimplify natin, we have angular velocity divided by the phase shift constant. So we have here the equation for the phase velocity, which is also the same with the velocity rin na isang na derive natin in the topic 1, transmission line. Yung group velocity naman, it is the rate at which the wave propagates through the waveguide. Yung kabuuan na, yung lahat ng signal na nasa loob. So it is the rate at which a modulated envelope travels compared to the carrier alone. This modulated wave travels through the waveguide and is defined also as the velocity at which information signals of any kind are propagated. Any kind of information signal, lahat ng nasa loob ng waveguide. So by equation, it is equal to the square of the speed of light divided by the phase velocity. So the phase velocity and the group velocity are somehow computed in terms of each other. So the velocity of modulated envelope is usually lower than the carrier signal. Okay, in terms of frequency naman, as mentioned kanina, there is just this frequency where signals can propagate through a waveguide. that frequency that limits the propagation of other signal is called the cutoff frequency. So as seen here, okay, at cutoff frequency, ganyan na lang po yung behavior ng signal. Pero yung mga low frequency above cutoff will provide this reflection of signal. Habang yung frequency tumataas kesa dun sa lower, nagiging medium siya. Okay? Nagkakaroon siya ng mas malaking signal hopping or reflection. The higher the frequency, mas malaki yung ating angle of reflection sa loob ng signal. Pero lahat ng frequency which is lower na dito sa sinet na cut-off frequency, wala na, dead signal na po sila. For the cut-off wavelength, this is defined naman as the smallest free space wavelength that is just unable to propagate in the waveguide. Okay? Yung hindi na siya makapropagate sa loob in its smallest value. Sa bawat klase ng waveguide, let us recall, may iba't iba tayong cut-off frequency and cut-off wavelength equation. So for rectangular, we have here the speed of light divided by 2 times A, where A, ito yung ating dimension that is larger than dun sa ating nasa kabilang wall. So basta A will always be the large internal dimension. And yung ating cut-off wavelength is twice nitong large dimension natin or twice of A. So for circular waveguide naman, our equation is for the cutoff frequency 1.8412 times the speed of light over 2 pi times A. And the cutoff wavelength is 2 pi r divided by k times r. Okay, so actually, the KR here, hindi kayo magka-cancel ng R dyan kasi itong R na to is the radius. Tapos yung KR naman natin, yung kinukuha nating value mula sa Bessel function table. So usually, yung mga problem solving dito, mga direct substitution na po yan. Okay, so review ulit natin. May mga modes of propagation sa loob ng waveguide. Okay, ang hindi gumagana sa kanya is the TEM. Okay, so ang basic na operation niya is the TE, transverse electric, and the TM, transverse magnetic. So pag sinabi nating transverse electric, katulad nito, the electric field is the one that is perpendicular to our surface. And for the transverse magnetic, okay, it's the magnetic field that is perpendicular. So ganyan yung itsura ng wave propagation nila. Ito yung isa pa niyang image. So here we have the components of electric field and magnetic field for the electromagnetic wave. We can see here yung ating electric and magnetic direction for the X, Y, and Z axis. Nagagamitin to present yung ating mga iba't ibang modes. So dito, tatandaan lang po natin yung ating conditions. In TEM mode, both the electric and magnetic fields are directed components. And each of them is perpendicular to each other. Okay, so kapag vertically polarized, si electric field ang naka-vertical, si magnetic field yung naka-horizontal, and vice versa. For the transverse electric field, only the electric field is purely transverse to the direction of propagation, and the magnetic field is not purely transverse. Kaya kung makikita nyo rito, okay, si electric field natin ang naka-zero kasi kapag ang analysis po dyan, bakit siya zero? Kasi nakakontra siya sa direction ng propagation or naka-perpendicular siya to the ground which is in opposite direction. Kaya zero yung connotation sa kanya. Wherein yung magnetic field natin, it is not equal to zero kasi hindi siya nakakontra doon sa ground direction natin. For the transverse magnetic, baliktad lang po. Si electric field ang hindi equal sa zero kasi hindi naman siya directly perpendicular. At si magnetic field naman ang naka-zero kasi it is the one that is directly perpendicular to the propagation. So, yung modes natin, ina-identify siya ng Institute for Radio Engineers as TEMN or transverse electric waves. Okay, and TM, M, N for the transverse magnetic waves. Okay, so kaya TE and TM. Wherein M and N, they are the number of half wavelengths of intensity for the electric or magnetic field that exists between each pair of walls. So depende kung ano yung designation ng M and N kapag ang ginagamit mo ay TE or TM. Okay, so syempre kapag TE, ang M is the electric field, ang N is the magnetic. Sa TM, M is the magnetic, N is the electric field. So yung N, siya yung nasa dimension B, yung M, siya yung nasa dimension A. So pinaka-dominant mode, that is TE10. It is the most natural mode. Okay, that allows the smallest possible size waveguide for a given frequency of operation. So it acts as a high-pass filter and nag-allow lang for frequencies above the cut-off frequency. Ang range ng frequency for the TE10 is the cut-off frequency and twice of the cut-off frequency. Okay, this is our illustration of the propagation modes for the TE. Okay, showing our electric field kung ilan siya sa loob. At kapag TE10, you have one electric field shown here. Okay, kapag TE20, you have two on the positive and negative direction. Kaya ganyan naman ang kanya itsura. Then habang dumadami po, okay, yung ating mga modes of propagation, mas nagiging complex yung illustration po ng ating signal. And this is yung kanyang isa pang dimension, okay, as viewed sa ating 3D system. We have the electric field view for the TE1 mode and the magnetic field view. Okay, and this is the TE20, kaya dalawa na po iyan. Okay, tas wala dito. The TE01 na ang pinakita naman po dito is yung ating magnetic field na view. Okay, so dito po is yung iba pang view niya in terms of the magnetic field naman. Okay, so this is just another view showing dun sa color ng electric and magnetic field for their propagation inside our waveguide. So kung makikita ninyo, okay, so this is TE10. Okay, kita rito na may paisa-isang signal na lumalabas. Then dito we have TM11, wherein ito yung pinaka-H field natin, and this one is our E field. Okay, rules of thumb para sa waveguide natin. The TE10 mode of propagation should be the lowest mode that is supported, no lower than that. Okay, then the width or the widest internal dimension of the cross-section determines the lower cut-off frequency, at ang size po dapat dito is 1/2 wavelength. You will observe na ang mga size required for any metallic medium or for any medium of communication, even from the start of the topic antenna going to radio wave and to the transmission line na first topic natin, the standard size is half wavelength and the minimum size is quarter wavelength. So dito, it's always 1/2 wavelength of the lower cut-off frequency. The TE01 mode occurs when the height equals 1/2 wavelength of the cut-off frequency. And for rectangular waveguides, yung 20 po natin, okay, it only occurs when the width equals 1 wavelength of the lower cut-off frequency. Kasi nga, it's times 2 na, kaya dalawa na po sila. 1/2 wavelength times 2, kaya 1 wavelength po dito sa TE20. Okay, so mula sa umpisang discussion natin, lahat ng klase ng transmission medium ay may impedance. So dito po sa waveguide, meron din po tayong impedance. It is just that mas mahirap siyang i-measure as compared dun sa mga transmission line na alam mo na nagdedepende dun sa material inside the medium. With the waveguide, nagdedepende po siya doon sa mga signal na nasa loob ng medium. Kaya nga 'di ba doon sa table natin kanina, in transline, we have characteristic impedance. In waveguide, we have wave impedance. So saan gine-generate itong impedance na to? Okay, so it can be generated by using the voltage to be the potential difference between the top and bottom walls in the middle of the waveguide. Then we take the value of the current to be integrated value across the top wall. So when you have voltage and current, it gives us the ratio, which is the impedance. So doon siya sa wave strength kumukuha, not on the physical properties of the waveguide. So the waveguide is also utilizing the voltage, and then it use the power flow within the waveguide. So kung meron kang voltage, meron kang power, meron ka ring equation giving us the impedance. And it can be determined by taking the ratio of the electric field to the magnetic field at the center of the waveguide, wherein we all know that the ratio is also the impedance. So yun yung main difference niya in transline. And that the impedance is a factor of 2 of the free space impedance, factor of 2 lower, factor of 2 higher. That is why its range is from 190 to 750 ohms. That's the usual range of waveguide impedance. Then, we also have waveguide reflection. So, ang sabi rito, to obtain the optimum power transfer between a waveguide and its source load, the impedance of both items at the junction should be the same. Then, when the impedance of the waveguide is not accurately matched to the load, nagkakaroon din po siya ng standing waves, and not all power is transferred kasi nagkakaroon ng junction loss. Yung loss na yon ang pinepertain dito na source ng reflection para dun sa signal na nababawas for maximum power transfer. So similarly, when a source is providing power to the waveguide and there is an impedance mismatch, then it is not possible for all the available power to be transferred. Though sinasabi natin na bakit nagiging loss yung reflection, reflection naman yung mode ng signal sa loob ng waveguide kasi reflection happens before the signal actually propagates inside the waveguide. It may happen doon sa junction, it may happen mula pa lang doon sa ating transmitter papasok doon sa ating waveguide. So, that reflected signal now represents our loss. So, paano minamatch yung ating impedance mula doon sa junction na yon or mula sa load papunta sa waveguide para magkaroon ng maximum power transfer? There are 3 ways. We can gradually change the dimension of the waveguide so that it would fit doon po sa size na meron doon sa connecting point niya from the transmitter. Or we can use a waveguide iris. So pag sinabi nating waveguide iris, basically isa po siyang obstruction doon sa ating waveguide na nilalagay para po yung waveguide natin ay maging inductive or capacitive. Or kaya maglalagay tayo ng waveguide post or screw. So this is how we do yung ating impedance matching using yung pag-gradual change. So, titignan mo kung yung usually ina-apply ito sa mga flared horn antenna natin. Okay? Either in E-plane, in H-plane, pyramidal, o kaya conical. So, nasaan yung adjustment? Dito po sa point na ito. So, diyan pa lang, kailangan perfectly match na yung ating waveguide doon sa kanyang sa kanyang equipment or material kung saan sila nagko-connect para ma-ensure na walang reflection diyan sa part na yan, yung kanilang connecting point. Also, kapag gumamit tayo ng iris, okay, so as mentioned, it is an obstruction within the waveguide, but it provides capacitive or inductive element. So, the obstruction iris is located in either the transverse plane of the magnetic or electric field, and a waveguide iris places a shunt capacitance or inductance across the waveguide. An inductive waveguide iris is placed within the magnetic field. Pakitandaan po ito kapag inductive sa magnetic field, kapag capacitive sa electric field po nilalagay yung iris. So this can be susceptible to breakdown under high power conditions, particularly the electric plane irises as they concentrate the electric field. Okay, so it can pose or it can limit power handling capacity of the waveguide. So, pwede siyang nasa isang side, pwede siyang nasa taas lang, nasa baba lang. Okay? Or pwede siyang nandoon sa buong part ng wall, katulad po nito. Okay? Pero kapag nasa lahat siya ng part ng wall, nagiging na siyang lamp circuit. Okay. So, dito, pinapakita na nilagay po siya dito sa side ng wall. So, kapag nasa side po siya, ang function po niya is as inductive reactance. Kapag po siya nandito sa top and bottom ng wall, capacitive reactance. Kapag po siya dinistribute mo sa lahat ng part ng wall, it now becomes a lamp circuit. So, kailan siya nagiging inductive and capacitive? So, at resonance, the iris acts as a high impedance shunt. Okay? Above or below resonance, the iris acts as a capacitance or inductive reactance. So, nagiging siyang lamp constant circuit kapag naka-resonant frequency siya. Kapag above or below the resonant frequency, doon po siya nag-act as this filter. So, ginagamit po natin ang iris para lang ma-establish kung anong loading yung gagamitin natin para ma-match mo yung ating waveguide impedance doon sa load kung saan mo siya kinoconnect. Then, yung paggamit naman ng post or screw, technically, talagang ano siya, screw na nilalagay mo sa loob ng waveguide, katulad nito. Ayan po yung screw niya. At yung position nun ay may impact po doon sa ating waveguide. So, the waveguide post or screw is made from a conductive material, and to make it inductive, it should extend through the waveguide completely, making contact with top and bottom walls. Kapag sinagad mo po siya from top to bottom, inductive yung kanyang behavior. Kapag naman siya nakatrue lang or kalagitnaan, capacitive po ang behavior ng screw. So that is how science works with waveguide. Screw lang yan, iris lang yan, pero the property of the materials used para po dito ay nakakaapekto sa impedance matching natin. And that is the basic reason why you diniscuss nyo ito sa inyong material science because of that property. Okay, so the characteristic impedance of waveguide is analogous to SAO o parallel wire transmission line and closely related to SAO o free space. Okay, kasi 'di ba yung sa parallel wire natin, somehow nagre-range yung kanyang mga characteristic impedance between mga 250 ohms hanggang umaabot pa siya ng up to 500 ohms. Samantalang na-mention na itong free space natin, 377 ohms, at ang SAO ng waveguide nagre-range from 190 to 750 ohms. Kaya sinabi na analogous siya, at yung characteristic kasi niya is also affected by ng mga factors which you can compare doon sa nangyayari sa ating transmission lines at sa free space. So, two waveguides with the same length A dimension but different length B dimensions will have the same value of cutoff frequency and the same value of characteristic impedance. Why? Because the cutoff frequency depends on the length A dimension of the waveguide. If these waveguides are connected together end to end and an electromagnetic wave is propagated down them, discontinuity will occur at the junction point. Doon magkakaroon ng reflection at doon magkakaroon ng ating impedance mismatch because of the losses introduced in this junction point. So, the same concept. Pare-pareho lang po yan sa lahat ng klase ng transline. Kailangan lang na-summarize mo saan sila nagkakatalo. Okay? In terms of propagation, in terms of material, in terms of factors affecting them. So basically, ganun lang po kasimple ang ating waveguide. Okay, then when we compare that dito sa fiber optic cable natin, okay, so saan sila nagkakaiba? As we all know, pag sinabi nating fiber optic, light yung nagpo-propagate sa kanya. And this light has a certain range of frequency lang at iyon lang yung gagana sa fiber optic cable natin. And yung parts ng fiber optic cable natin, Okay, depende kung siya ay single fiber o kaya multi-fiber. So itong multi-fiber po natin, hino-hold po siya ng iba't ibang mga materials, okay? Para hindi po siya magkaroon ng leak kasi po kapag hindi na-handle properly yung kanyang temperature, yung strength po niya, malagkit po ang mga parts niyan. Nagsisimulang lumabas yung mga oil ng fiber po diyan. At delikado, kailangan properly mo siyang na-handle kasi may napatay na po na mama because of improper handling ng fiber optic cable. Dahil sa sobrang nipis niya, naka-micrometer, tapos natusok yung dulo ng kanyang hintuturo. And yun po yung dumaloy sa loob ng katawan niya at yung fiberglass na yun dumaloy hanggang puso niya at iyon yung naging cause ng death ng tao na yun. Okay, so dapat tama yung pag-handle mo sa fiber optic kasi its main material is silica or glass. So ito po yung kanyang mga materials mula sa dulo, a polyethylene jacket, yung black na nagsusupport lahat ng mga parts na nasa loob ng fiber optic. It has a rip cord. Rip, ayan, hiwa-hiwalay siya. Okay, so it is used para magkaroon ng pampasikip po dito sa part na ito. Iyan po yung tinatanggal mo rin kung gusto mo mag-loose ng konti. Okay? Yung strength yarn po natin, para lahat po yan ay pang hold in place ng ating iba't ibang mga wire po dyan. At yung strength yarn natin, meron siyang mga pinupuluputan pa po dyan sa loob. Then it has water blocking binders para hindi makapenetrate at hindi makapasok dyan yung tubig kung umulan or kung ano man. So protection pa rin siya. Okay, it has flexible buffer tubes. Ito na po yung mga pula, itim, blue na yan. Pang-hold ng group ng fiber sa loob. Then we have the optical fibers and the central strength member which holds them in place. Sa kanya iikot yan para lang for proper spacing lang po ng ating mga flexible buffer tubes po. Then, basically, ito yon kapag naka-single fiber po siya. Okay, so ito naman ang kanyang ginamit na jacket ay black polyurethane. Okay, then it has its strength member din. Yung strength member na yan, pag tinignan mo po, ito rin po yan, yung ripcord, yung strength yarn. Then we have the buffer jacket. Okay, then we have the silicone coating, the cladding, yung silica natin, and the core na silica din po. Okay, so ito yung pinaka-external optical fiber na nabubuo na po natin. Okay, this is how the fiber operates. Ito yung pinaka-basic block diagram niya. So, yung mga conversion na ginagawa ng fiber. From the information source, okay, so basically, ang dadaloy sa kanya ay digital signal. So, we have here information source na ita-transmit electrically. Then, we have the optical source na magko-convert na nung ating signal into optical data natin. Then we have the optical fiber cable, siya na yung magke-carry. Na sa dulo, meron siyang optical detector. Okay, then we have an electrical receiver. Yung detector, ide-determine niya the information. Tapos, ilalagay niya doon sa electrical receiver kung saan yung optical data i-convert na into electrical signal para it can be understood by yung destination or receiver. Para lang din po siyang block diagram of communication system wherein ito po yung ating transmitter. Ito po from the source. Tapos ang transmitter natin is electrical transmit and optical source wherein diyan nagaganap yung conversion of signal into a form suitable for transmission. In this case, ang form suitable sa kanya is yung optical data or optical signal niya at dadaan siya into a medium or channel. Since fiber optic communication, the FOC is yung ating medium. Then sa receiver, eto na po yon. The optical detector and electrical receiver. Dito mangyayari yung transforming the signal back into its original form. So from the optical data, gagawin na siyang electrical signal kasi doon gumagana yung layman's equipment natin in voltage and current. So conversion lang po ito ng voltage and current into light, into voltage and current. Okay, that's the basic block diagram for the optical fiber communication. So advantages and disadvantages in summary, it has greater capacity and high bandwidth. It is smaller in size and lighter weight, and it has low attenuation. There is electromagnetic isolation or immunity to environmental interference, and highly secure due to top difficulty and lack of signal radiation. Di nga ba si PLDT ngayon, ito na yung kanilang pinopromote talaga, the use ng fiber optics. Kaya lang sa sobrang bagal nila, nauunahan sila ng Converge at kung ano-ano pa. Ang problema naman kay Converge, tanggap naman ang tanggap din ng customer na hindi chine-check yung capacity ng kanilang mga box sa mga poste. Minsan bayad na si customer, hindi na nila makokonektahan kasi wala na palang available slot. Ayun po, nagaano sila, consumer grabbing na tinatawag, na tanggap ng bayad, pero hindi na kaya ng kanilang mga system. Okay, so it has greater repeater spacing, which is 10 times of kilometer at least, as compared sa conventional copper wire po natin. Then disadvantage niya, syempre dahil complex na yung sistema niya, it is expensive over short distance, at saka mas maganda sana siya kung pang malayuan kasi kung short distance at putol ka ng putol, yung splicing is another questionable part ng fiber optic dahil doon nag-i-start yung losses natin. It requires highly skilled installers na may training way back 2000 before 2010 when we trained in Meralco for the splicing of fiber optic. Nung time na yon, yung pang-splice cost more than 600,000. Pero ngayon, mas mura na kasi marami na tayong mga materials. At yung training na yon, that is only 2 hours na seminar at saka konting viewing pero not exactly hands-on. The training is 1,500 na. Ganun siya kamahal nung time na yon. Pero ngayon, ang dami ng mga OJT at saka company na nagpapa-experience talaga na gumamit ng mga splicer and other equipment aligned with the fiber optics. Then it has adding additional nodes is difficult kasi nga it will require yung intensive skill ng tao. Okay? At saka nung mga equipment na kailangan para sa kanya. So these are the tools and equipment for doing fiber optic cable splicing and connections. So may iba-iba siyang tawag, the buffer tube cutter, the needle nose pliers, fiber scribe, twisters. Okay? Even po yung tissue na ginagamit sa ating fiber optic during that time ng training namin, the tissue cost parang 20 pesos per sheet of tissue kasi 100% wala siyang hibla na makukuha. Napaka-perfect ng kanyang pagkagawa. Yung panglinis ng fiber. Okay? Dito, dati nung time, parang ganito lang din yung size niya, pero mas mahal pa daw siya sa Honda car dati. Yung isang equipment na yon. Kaya, nung sumisibol pa lang ang fiber optic sa Pilipinas, kapag ikaw ang may hawak nito, lagi ka at magte-test ka sa field or kung saan man, may gwardiya raw na nakabantay. Kasi sa sobrang mahal ng equipment na yan. Okay, pero ngayon, mura-mura na siya kung makikita natin. Okay, may mga fiber optic test equipment na to, similar dun sa kanina. Okay, so 81,000 na lang. So, na lang. Pero wala tayo sa lab. Okay, ito mahal pa rin. Cable tester, 238,877 and so on. So, pero at least, mas mura na siya compared dati na 600,000. Okay, so, complex siya kasi iba-iba rin yung kanyang mga connectors. So, from the Bionic, standard connector, hanggang sa E2000 connectors, ganyan kadami yung connectors na ginagamit sa fiber optic. Kaya, Compared sa iba-ibang transmission lines natin, ang pinaka-sophisticated kapag kinoconnect ay si waveguide because yung mga couplers na ginagamit at saka itong connectors ng fiber optic. Okay? Tapos, challenge pa na i-identify mo at tatandaan mo kung anong klaseng connector sila. Ayan, yung mga Biconic, yung mga E2000 kanina. So, siguro kapag talagang iyan yung trabaho mo, kabisado mo na yung tawag sa kanila. Okay? So, bawat isa may specific application for the waveguide connection. Then, for the mode of propagation sa waveguide, alam natin, syempre, andyan naman yung simple, mula sa mode niya, kita na agad kung bakit. Sa multi-mode fiber, marami pong signal sabay-sabay na dumadaloy sa loob ng isang fiber optic. Kapag single mode, okay, strike through lang siya sa center ng fiber natin. Then, kapag sa step index at sa graded index naman po, okay, so it is on the nature ng ating material na ginagamit sa loob. Kung makikita nyo dito sa ating step index, so reflection yung gumagana sa ating signal. Yung index of refraction natin provides this reflection. Samantalang sa graded index po natin, okay, yung index of refraction natin, nagde-decrease ng mga radial distance ng ating signal. Tapos pagdating sa cornea, nag-i-increase. Okay? Nagpo-form siya ng ganitong shape po natin kung saan nagta-travel yung light natin faster near the edge of the core kesa dun sa center ng core po natin. So, it forms na yung ganitong itsura ng ating signal. Nagkakaroon na tayo ng curved path. Unlike dito, meron tayong linear path para sa ating signal. That is because of the index of refraction. So, to understand further, ito yung pinaka-comparison ng single mode and multi-mode, tsaka mamaya yung ating graded at tsaka step index. So, in single mode, fiber, only one mode can propagate through the fiber. Given na yan. So, sa multi-mode, it allows a large number of paths or modes for the light rays traveling through it. Kaya nga, multi. Sa single, it has a smaller core diameter and the difference between the refractive index of the core and cladding is very small. Sa multi-mode, it has larger core diameter and refractive index is larger than single mode fiber. Sa single mode, there is no dispersion or degradation of signal during propagation. Sa multi-mode, okay, meron siyang degradation kasi nga naka-multi siya, the behavior is not that linear. And ang disadvantage ng single mode, launching of light and connecting of two fibers is difficult. Okay, and sa multi-mode may advantage siya na yung disadvantage ng single mode ay advantage po niya. Okay? Then sa single mode, installation is difficult as it is more costly. Samantalang sa multi-mode, fabrication is easy and the installation cost is low. So, this is the comparison of single mode and multi-mode. For the step and graded index naman, which is a function of our index of refraction. So, sa step index, uniform po. Okay? Mula sa core natin, then suddenly, changes po ito at core cladding boundary. Then, dito po, sa refractive index ng graded natin, it is not uniform. And it is maximum along the axis of core and decreases towards core cladding boundary. So, basically, uniform versus non-uniform. Okay, so in step index, pulse distortion is present. Dito sa graded, pulse distortion is minimum. Na marirealize nyo na parang somehow, pagdating sa fiber optics, okay, so mas nagiging advantage pa po yung ating iba't ibang index depende sa pangangailangan or yung purpose mo for communication. So, iyon yung pagbabatayan mo dito. Alin kailangan ko? Step index or graded index? Okay, so step index, pwede siya for single mode or multi-mode. Samantala si graded only for multi-mode. Okay, step, it can be manufactured easily. Okay, sa graded, manufacturing is not easy kasi marami nga siyang iba't iba yung index of refraction sa loob ng fiber optic. Then number 5, it has high numerical aperture. Samantala dito, low numerical aperture. Attenuation is higher for step, attenuation is lower. Then lower bandwidth for step, higher bandwidth for graded. And reflection losses are present sa step, reflection losses are absent dito sa graded. So, titignan mo muna as engineer, ano yung requirement ng system design ko. Then, ito yung mga checklist mo, which one will give you mas maraming check kaysa mas maraming X. Then, yung mga X na yon na hindi na-satisfy, doon lalabas yung pagiging creative mo as engineer kung paano mo siya ito troubleshoot para ma-overcome mo yung mga X na yon. Okay, so these are the different measures ng ating cladding core, ng core diameter, as well as the attenuation for the single mode, multi-mode, and dalawang size ng multi-mode for the core cladding. So, the cladding diameter for single is 125 micrometer. For multi-mode, it's the same. And the same for the last column. But for the core diameter, nagre-range siya from 8 to 10 micrometer per single mode, 50 for multi-mode, and 62.5 for its other core diameter. Then the attenuation depends on the wavelength used in our fiber optic. So for this 850 nanometer wavelength, no attenuation for single mode. This is the measured attenuation 2.5 and 3.5 for the multi-mode of different core diameters. But for the 1300 and 1310 nanometer wavelength, okay, so tumataas po yung ating attenuation. And for the 1550 nanometer, okay, it is negligible for the part of the multi-mode. Okay, so for the losses in our fiber optic cable, so dito sa unang picture, pinakita na halo-halo yung mga losses na kawawa naman fiber optic kapag pinaranas mo sa kanya lahat ng loss na yan. So we have here the absorption loss. Okay, so absorption loss happens because of the same amount of the same material always absorbs the same fraction of light at the same wavelength. Yun yung pinaka-concept niya. Kapag pumasok na yung light na yan, kahit ano pa yan na light, mag-a-absorb siya ng the same amount. Parang function na niya yon na hindi lahat ay makakatagos diyan sa fiber optic. There is certain fraction na maiiwan. At kapag i-compare na naman po natin uli siya sa ating metallic transmission line, it pertains sa standing wave, yung signal na hindi na nakaalis doon sa part na yon. Kapag kinompare mo siya sa radio wave propagation, siya yung bubble frequency na nakikita natin na nandun sa air na nagpo-form lang siya ng loop. Okay? Another loss is the splicing loss. Yung pinutol mo siya, tapos hindi mo siya na-connect properly. Okay? So, yung splicing loss na yan, may iba't ibang klase pa siya, itong nasa kanan. If it is properly spliced, wala po tayong loss. Pero kapag hindi siya properly sliced, it can have end not square cut. Kaya ayan, dyan nagpo-produce yung splicing loss. Misaligned. Okay? Both ends are not polished smoothly. So kahit pagdikitin mo yan, meron pa ring exit ang light dyan. Pinagdikit mo, pero meron pa ring gap or space in between them. And nag-splice ka, pinag-connect mo, pero magkaiba naman yung diameter. So these are the possible scenarios for the splice loss. Also, we have impurity of the material. Kung pinanood nyo yung mga videos na nakalagay sa bawat topic. Yun sana, panoorin niyo yung mga nilagay doon na reference videos for additional information. Nakikita natin doon sa isang video doon kung gaano ka-tedious yung process to produce yung silica para doon sa fiber optic na yon at para makuha yung tamang diameter. Kapag hindi proper yung treatment natin in the manufacturing of fiberglass, nagkakaroon ng impurities, and this is another source of loss po. Yung impurity na yon, pwede siyang mag-cause na yung signal ay hindi properly makapenetrate doon sa fiber optic. Iba-block niya. Then we have the bending loss, which can be macro kapag sobrang binend mo, or the micro. Okay? Then, kapag may bending loss ka, hindi na magta-travel yung signal ng diretsong-diretso dyan or ng yung kanyang reflection sa loob ng fiber optic, hindi mo ma-achieve perfectly. Okay? We also have the scattering loss. Okay? This is because the wave interacts with a particle in a way that removes energy in the directional propagating wave and transfer it to other directions. Di ba nga, pag sinabi natin scattering, ayan, kinakalat niya at napupunta sa ibang direction yung signal. In which, pag binalikan natin sa radio wave propagation, somehow it becomes an advantage because even those areas that are not primary area, nandun sila sa secondary receiving area o kaya intermittent receiving area, nakaka-receive sila ng signal. Pero with fiber optic, it is considered one major loss. Okay, another losses po natin is itong ating chromatic dispersion. So dito, yung signal natin ay na-spread siya over time because of the different speeds of light rays po natin. So iba-iba yung speed ng light rays natin at kumakalat yung ating light rays because of these different speeds. Then we have the modal dispersion. So spreading of the signal over time because of the different propagation modes naman. Kung dito sa chromatic dispersion, this is because of different speeds. Dito po sa modal dispersion because of the different modes from its keyword na modal dispersion. Okay, so these are the parameters of fiber optic which you will realize na na-discuss na rin po natin doon sa radio wave propagation natin. So parehong-pareho lang po sila. Let's just go through. So we have the Snell's law, which is still the N1 sine theta 1 equal to N2 sine theta 2, wherein N1 is and N2 are the index of refractions of the mediums we use for fiber optic. Then the theta 1 is the angle of incidence and theta 2 is the angle of reflection. Then we have here the index of refraction, which is equal to the square root of relative permeability times the relative permittivity. Okay, then another parameter is, this only shows yung iba't ibang internal reflection natin na na-discuss din natin before. Okay, so sa ating radio wave propagation. So we have critical angle. Okay, so it is the angle formed para magkaroon ng reflection from one medium to another. So we have here critical angle is equal to arc sine of the second medium index of refraction over the first medium. Okay, then we have the numerical aperture, the measure of the light gathering capabilities of an optical fiber na kinukuha rin natin mula sa ating mga index of refraction. Then we have the cone of acceptance. So it is the angle formed kapag yung light po natin is nagtatraverse na over the fiber optic. So it is equals to 2 times the critical angle po natin. Okay, then we have the core radius for single mode fiber with an equation of 0.383 lambda over the numerical aperture. Then another parameter po natin is the energy absorbed or emitted in fiber. So this energy natin has a unit of um, electron volt or joule, and it is equal to the Planck's constant. Ito po yung Planck's constant. Kung hindi kayang tandaan, sa board exam, sa calculator nyo, nandun yan. Tuklasin nyo anong function yung pinipindot para lumabas yung Planck's constant. Then we have the frequency of light emitted in hertz. And note that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Then for the optical power in fiber optic, the equation being PT times 10 raised to negative attenuation times length divided by 10. Okay, so idadagdag na naman ito sa mga formula na sana ay matandaan nyo hanggang sa kayo ay mag-board exam. By the way, last week, anong araw ba yun? Tuesday yata? Itong week na to, or Monday this week, we had a consultation with PRC board examiner for ECE. At ayun, hindi pa rin sure kung may board exam this coming April. So dumadagdag pa yung mga hindi nakapag-board exam nung October kasi dapat may board exam ng April, tapos October, tapos magbo-board exam ngayong parating na April. Kaya lang, naiipon sila. Why? Kasi isa palang requirement para matuloy ang board exam, kailangan yung magbo-board exam ay merong negative swab test, which is costly. Okay, so yan, lapit na tayo matapos. We now have irradiance, the power per unit area in laser. So it is equal to power over area. Ganun lang siya mula sa definition itself. Then we have the radiance, measurement of the strength of light source such as in laser, wherein the equation is power over the solid angle or is the radian multiplied by the aperture area of laser output. I wonder kung paano nyo talaga siya matatandaan kasi kapag nasa classroom, mapipilitan talaga kayong kabisaduhin kasi may exam, tapos close formula. But now na hindi tayo nagkikita at wala namang exam, please discipline yourself na lang para somehow matandaan nyo itong mga equations na ito at magamit just in case may problem solving kung kayo ay magbo-board exam. Okay, next slide. We have the light sources. So ito naman yung, I think kaya kasama rin siya sa inyong topic sa math sci ay dahil sa mga materials used for the light sources at sa iba pa nating light detectors ng ating fiber optic. So even from electronics subject, na-discuss na natin itong LED, okay, na ang material niya ay aluminum, tama ba class? AlGaAs. What is Ga? Class, what is AlGaAs? Math sci.
Hindi ko po alam yung GA, ma'am.
Ga is gallium.
Ay,
What is Al?
Aluminum.
Aluminum.
Gallium.
Gallium.
What is As?
Arsenide.
Okay. Okay, then what is GaAsP?
Gallium arsenide.
Arsenide phosphide. Okay. So, kaya yan nasa inyong math sci. So, in LED, light is emitted when holes and electrons recombine. Anong kulay po ng LED ang pinakamahal?
Yung bright white po.
Hindi po. Okay, ang pinakamahal na LED is yung kulay blue. Okay, kaya kung makikita nyo sa mga experiment natin, usually gamit natin, it's either yung white, yung red, at saka yung green. Kasi napaka-costly ng blue. Okay, then we have the injection laser diode. So it is similar in construction as LED, but ends are highly polished to reflect photons back and forth. So, tsaka mas mahal po ang injection laser diode. Okay, pero ang pinakamahal is the laser. Okay, laser stands for light amplification by stimulated emission and radiation. So this light can be coherent, narrow beam. Okay, it has high output power for amplification and it has narrow line width because only few wavelength will experience a positive feedback and get amplified. And we call this optical filtering. Huwag nyo ididiretso sa mata nyo ang laser. Kung hindi nyo na makikita ang kinabukasan. Okay? Kaya nga di ba napaka-costly kapag nagpapa-opera at nile-laser yung mata. Even kapag may katarata na, di ba there are two ways para i-ano yung cataract. Pwede siyang i-scrape o kaya pwede siyang i-laser. So, mahal yung laser kasi madali lang. Madali lang yung tunawin yung namuong black sa mata mo. Kaya lang, delikado kaya mahal siya, highly skilled din yung gumagamit no laser beam na material or equipment kasi may mga ugat sa mata na hindi niya pwedeng tamaan. So, comparing the LED to laser in terms of output power, sa LED, linearly proportional to drive current. Sa laser, proportional to current above threshold. And the drive current nito ng LED is 50 to 100 milliampere peak. Samantala sa laser, 5 to 40 milliampere lang po. The coupled power is moderate in LED, high in laser. The speed is slow for LED it's slower than laser, 0.5 microseconds, and laser is faster than average LED. The output pattern ng LED is wide. Okay, mas kalat yung signal, yung ilaw niya as compared sa laser na naka line of sight po siya. Yung bandwidth ng LED is moderate, si laser is high. And wavelengths is 0.66 micrometer to 1.65. Samantala si laser, 0.78 to 1.65 micrometer. Then, spectral width, 40 nanometer to 190 nanometer. And ito naman, 0.00001 to 10 nanometer lang. Fiber type ng LED, multi-mode. Okay, sa laser, single and multi-mode. Ease of use, it's easier to use laser than the LED than laser. Yung lifetime ng LED is longer than the laser. Okay, then the cost ng LED, okay, depending on the system size and requirement, kasi it is not just an ordinary LED for fiber optics. It can be $5 to $300 from the source. Kinumpare ko to sa iba, almost the same lang din yung range niya. And for the lasers, 100 to 10,000 depending on system size and requirement po. Okay. Yung dalawang diode naman, comparison. Okay, so ganito yung itsura ng diode kapag ginamit siya sa fiber optic. Samantalang ganito yung itsura ng ILD natin na ginagamit for the fiber optic. So, ito, gumamit siya ng LED dito para sa kanyang experiment with fiber optics. So, si LED, it has lower efficiency compared to ILD. Kaya mas mahal si ILD. Okay? It has a slow response rate compared to ILD. The data transmission, laging low, laging talo si LED. For the construction, simple si LED, si ILD ay complicated ang construction. Kapag tinignan mo pa lang dito, okay, ang dami na niyang, yung liit niya na yan, okay, ang dami niyang parts sa loob. And it has higher distortion level at output. Si ILD, it has lower distortion level at output. Okay, high dispersion, low dispersion, incoherent beam, and coherent beam. So kung makikita nyo, mas kalat po yung ilaw ng LED kesa dito sa ating ILD. Okay, for the detectors, electronics pa rin po yung ginagamit natin. It can be PIN diode or APD, avalanche photodiode, positive intrinsic diode. Okay, so dito, ang ginagamit niya ay the photons are absorbed in the intrinsic layer and sufficient energy is added to generate carriers in the depletion layer for current to flow through the device. So as seen here dito, review ng electronics natin. Ito yung itsura ng pin diode natin. Okay? So it is similar to the normal PN junction diode except that it contains arrow to represent yung light or photons natin na magi-strike po sa kanya. Okay, so this is the circuit symbol natin and ito yung pinaka-junction niya sa loob. And for the avalanche photodiode, kung nare-recall nyo pa po sa inyong industrial electronics, it is a diode where photo-generated electrons are accelerated by relatively large reverse voltage and collide with other atoms to produce more free electrons. And the multiplication effect makes APD more sensitive but also more noisy than PN diode. So may pros and cons yung bawat isa sa kanila. So characteristic niya, ito yung itsura ni avalanche photodiode. High gain due to avalanche multiplication effect, increased noise. Silicon has high gain but low noise. And what is this? Silicon, what is IN class? What is IN material? Is it indium, gallium, arsenide, APD? Okay, so ito yung ginagamit niya na diagram. Okay, para dito sa ating avalanche photodiode. So for light sources, we have LED, ILD, and laser. For the light detectors, we have pin diode and the avalanche photodiodes. Okay. Oh. Okay, wait lang. Okay, for the link budget po natin, kunin ko lang yung slide. Okay, for the last slide, for this semester is the link budget for fiber optic cable. So, basically, pag sinabi nating fiber link budget, it is a way for describing yung mga losses and other consideration para sa accurate performance ng fiber optic cable when it is used for communication system. So the link budget will give us the actual loss value for all the processes involved dito sa ating communication system. And itong link budget equation natin can be used kapag hindi available yung optical time domain reflectometer. Okay, so pero kung meron kang optical time domain reflectometer na equipment, so madali na po yung ating pag-compute ng link budget for FOC. So there are two steps na ginagawa po dito. First, you have to estimate the total link across an existing fiber optic link in the fiber length and loss variables. So ito po yun, yung mag-estimate ka ng total loss link mo sa loob at sa haba ng iyong connections. Then estimate the maximum fiber distance or fiber length if the optical budget and loss variable are known na. Kapag alam na natin to, okay, compute na for the fiber length. So ano yung components natin? So ito yung sample ng utilization ng ating link budget for FOC. So ito mula dito sa ating electronic interface ng transmitter natin, may connector. So lahat yan pwedeng mag-produce ng losses at makakontribute doon sa ating link budget. So equation na dalawang tatandaan, link budget is equal to the fiber length in kilometer multiplied by the fiber attenuation per kilometer. So this is dB per kilometer. So dito pa lang sa una natin, kilometer makakancel, matitira dito ay dB. Plus splice loss times the number of splices. So, i-check mo ilang splicing yung ginawa within the length na yan. So, splice loss is dB times the number of splices, that is unitless. So, dB pa rin po ito. Plus, connector loss in dB times the number of connectors. So, wala itong unit, kaya dB pa rin ito. Plus, the safety margin. Okay? Yung safety margin or safety factor, binibigay po yan depende sa kung ano yung material mo na ginagamit. Pag sinabing safety factor or safety margin, it is also in decibel and it is yung ratio ng stress over the strength of material. So, pag sinabi safety margin, kailan pwedeng bumigay o kailan pwedeng bumaba yung value or yung strength ng material mo. So usually, ang minimum na safety margin or safety factor is 2. Ibig sabihin, for example, yung poste mo, ang carrying capacity niya na nakalagay ay 100 kilograms with a safety margin or safety factor of 2. In reality, kahit nahigitan mo siya sa 100 kilo, kaya po niya. At kung ang safety margin niya ay 2, ang actual capacity niya or actual maximum capacity is 200 kilograms. Pero, hindi mo kasi siya i-overload ng up to its maximum capacity kasi yung poste magbe-bend or magkakaroon ng degradation ng kanyang orientation from true north or hihilig. Hindi na siya naka-vertically straight. Kaya ina-apply yung safety margin. Tapos, paano mo malalaman na kailangan ng palitan yung isang material? Kapag na-reach mo na yung 2/3 ng safety margin or safety factor. Ibig sabihin, kung halimbawa ulit sa poste kanina, ang nakalagay sa specification niya, 100 kilograms load plus a safety margin of 2. So, ang actual capacity niya talaga is 200 kilogram. Pero, kapag nilagyan mo siya ng what is 2/3 of 200, what is 2/3 of 200 plus? 60, o sabihin na natin na 133.3 kilograms. Tapos nakita mo yung poste, humilig na siya ng konti. Okay? So, ibig sabihin na nag-incline na siya either to the left, to the right, forward, or backward. You have to replace na yung poste pero hindi nangyayari yun sa totoong buhay. Instead, ang trabaho lang is to put safety sign. Kapag naglagay ka ng safety sign sa anumang structure, okay, so may mga proper location pa. In the case ng link budget for FOC, naka-note po yon sa kanilang mga logbook kung ano na yung safety margin or na-reach na ba or na-exceed na ba. Kung sa poste po yan, ang paglalagay ng safety sign is 2 meters above the ground. 2 meters because it approximates the height of individual traversing dun sa ating poste at makikita niya ng line of sight yung safety sign na yon. So, malaking bagay itong safety margin po na yan. In our field, ECE, safety margin plays an important part kasi kung hindi mo siya i-consider, lagi mong ilo-load yung ating structure beyond its capacity. Okay? So, the link budget, ang unit po niyan ay decibel. Okay? So, another is yung fiber length. So, it's an optical budget minus link budget divided by fiber loss per kilometer. So, optical budget minus link budget, pareho yung decibel. Tapos, yung fiber loss per kilometer, decibel per kilometer. Makakancel yung mga 2 decibel mo, aakyat yung kilometer. Kaya kilometer yung length ng first expression po natin dyan. Okay, and another equation na pagdikit ko, fiber length is equal to minimum transmitter power minus receiver sensitivity minus the splice loss times number of splices. Okay? Then minus connector loss times number of connectors minus safety margin divided by fiber loss per kilometer. So, kapag in-apply mo po iyan, so yung fiber length po natin, ang unit po niyan ay kilometer. So, iyan po yung mga dapat matutunan ng mga equations. Sa handouts po ninyo, meron na po dong sample na problem solving for the link budget for FOC at saka yung mga equations na binigay po natin kanina. Okay, so that is the last slide for the topic. The floor is now open kung may question po kayo. It's now 9:15. Okay, so any clarification po? Kung may gustong i-share na experience, kung may tanong about the topic, at kung gising pa kayo lahat. Pasensya na natapos ang SEM natin na hindi ko kayo nami-meet sa morning. Kapag teacher nyo ako sa second SEM, expect ganyan pa rin po. Kasi we leave PUP at 7 p.m. Talagang hindi kaya ng signal ng PUP ang magklase doon. Kung hindi maghapon akong parang robot. Okay, so any question? Since siguro dahil review lang, naaalala nyo pa yung mga nakaraan. Okay, so
Yes, ma'am.
opo. Kung may tanong po, may clarification, basta po open yung GC natin ha, tanong lang kayo doon. Tapos,
Ma'am,
yes po.
yung presentation po namin na dapat magre-report, isend na lang po ba namin sa inyo?
Yes po.
Sige.
Yung pong hindi nakapag-present, pasensya na. This coming week po kasi ay kaya ako minadali. Hindi ko na rin kayo kayang i-meet this coming week sa dami po ng trabaho namin ngayon. Kagabi inabot kami ng halos 9:30 o mag-aalas 10 na sa meeting. Yung ngayon na minute ko kayo, actually, 3 yung meeting na tinapos ko bago kayo maiklase. Kaya medyo late din ako nakapag-join.
Thank you po, ma'am. Thank you po.
Okay, thank you din sa inyong lahat. Hindi ko man kayo nakita personally sa loob ng classroom. I hope yung GC natin ay maging instrument para kung meron kayong mga gustong erase na issues and concerns. Okay? So, for the last time, may I request